Assalamualaikum warahmatullahi wabarakatuh and good day everyone. Welcome back to our site for CHE 433 Thermodynamic. I would like to present about chapter 2, which is the properties of pure substances. For this first video, I will present to you the first subtopic related to the phase change processes of pure substances. Let's zoom in to this particular topic. In this topic, we will cover three different subtopics related to an example of phase change of water, latent heat, and difference between temperature versus specific volume diagram, as well as the pressure versus specific volume diagram, which commonly used in this particular chapter. The first part of here takes an example of phase change that happens for the water upon heating. The figure that is shown here is the temperature versus specific volume diagram of water during vaporization process that happen at atmospheric pressure of 1 atm. The water that exists at this initial stage, stage 1, which is at 20 degrees C, is at the compressed liquid state. This compressed liquid is heated up to 100 degrees C, where it reaches saturated liquid state 2, where it is about to enter vaporization stage. The vaporization stage takes place at constant temperature, where water changes from saturated liquid into saturated mixture, in this case state 3, where at this state both liquid and vapor exist in equilibrium. Once the liquid has been transformed into vapor, the water reaches saturated water vapor at state number 4. Beyond this point onward, the water is now at high temperature above 100 degrees C, in this case at 300 degrees C, where we can classify this state as superheated vapor. Now, speaking about the phase changing process, another important aspect to be considered is the latent heat. Latent heat is the amount of energy absorbed or released during a phase change process. For example, latent heat of fusion happens during solid-liquid transitional process, while for the latent heat of vaporization happens during liquid-vapor phase changing process. We can observe this latent heat by observing the flat line that occurs between saturated liquid and saturated vapor point. In the case of vaporization at atmospheric pressure 1 atm, the latent heat of vaporization is about 2256 kJ per kilogram. From the graph, we can see that the value of latent heat is changing with respect to the different pressure level applied on the constant system. Now, let's move to the next subtopic, which is about temperature versus specific volume and pressure versus specific volume, where in this case, specific volume is denoted by the small letter V. These are the two common graphs that you need to be aware on in this particular chapter. The temperature versus specific volume diagram represents the changes of temperature and specific volume with respect to its applied or constant pressure. So let's say if you are boiling up your water at atmospheric pressure, which is at typically 1 atm or zero point 0.1 megapascal, that means the process will follow the track for such pressure system. In converse, if you are boiling up your water at low atmospheric pressure, such as at the high mountainous area, then the pressure is expected to be less than 1 atm and follow the track according to the low pressure system. You will notice that this graph show upward trend of the track when pressure, the phase change takes place from the compressed liquid to superheated vapor. Now, another graph to be aware on is the pressure versus specific volume diagram, which, contrary to the temperature versus specific volume diagram, show the plot of pressure and specific volume at constant temperature. So, let's say if you keep your system at constant temperature or isothermal, then you are plotting changes of pressure throughout the phase change. You will notice that the track show an upward trend with respect to the specified temperature. For both graph of T versus specific volume or P versus specific volume, both graphs show identical region of compressed liquid, saturated liquid vapor region that is covered between the dome and the superheated vapor region. In both cases as well, the maximum temperature and pressure attained by a substance is revisited by both critical points where no distinctive difference could be observed between liquid and vapor.